Hello everyone, welcome to my channel. So in this video I will explain how to implement deep learning solution on Zynq Ultrascale Plus devices. So the lesson is based on approach offered by Xilinx. It's Vivado flow for Vitis AI library and allows to leverage deep learning solution for any Zynq Ultrascale Plus device. So the lesson covers three main essential questions for Vivado flow approach. So first of all, it's deep learning unit integration, deep learning engine integration into Vivado block design. So where I will explain how to set deep learning unit correctly for your for certain Zynq Ultrascale Plus device, how to connect it to processing system, and what kind of clock domains should be used. So on the second step, since we have already generated Vivado project and therefore XI file with hard information about our hardware is exported, we can go to the next step. It's a Linux deployment by utilizing PetaLinux. So in this step, I will explain how to deploy Linux, what kind of packages and receipts are needed in order to leverage Vitis AI library for deep learning solutions. And the last step, I will demonstrate two examples. It's object classification with ResNet 50 and object detection with YOLOv3 network and USB camera. So all information, all sources that are used in this lesson are available for free in my repository. The repository consists of folders, board folder. In board folder, there are several subfolders where is information that is needed by Vivado design. So it's a sys file, it's information about block design, and another TCL file for particular board. It's a file with set of instruction how to build a Vivado design and export XA file. Another folder, it's IP folder. Since in Vivado IP catalog there is no DPU model, this DPU model should be integrated externally. So this is how I'm doing by using IP folder. So it's sources for deep learning unit or deep learning engine. The next folder is a PetaLinux. So PetaLinux folder consists of also some subfolders devoted to certain board with settings for PetaLinux project. All necessary packages, all necessary receipts already for Vitis AI library already included into every subfolder. And the last folder is a scripts with some scripts that allows me to build either Vivado project or PetaLinux. So this folder is quite suitable not only because it allows to integrate easily your own Zynq Ultrascale Plus device, but also, by the way, Zynq 7000 device, but also this repository, this structure is quite suitable for version control. When you, for example, utilizes several different devices into your projects. Examples for this lesson will be run on the setup based on trans model from Zynq Ultrascale Plus to CG device on trans model and carrier board. The carrier board consists of several interfaces. It's a Ethernet and USB COM interface for communication, USB interface for USB camera, power supply, and microSD slot, since microSD will be used here as a boot device for Zynq Ultrascale Plus. More detailed information how to what to do in all these three sections are available on my website. So here can be seen three sections, completely the same. So starting with Vivado hardware design, Linux deployment, and finally, for example, Vitis AI library examples where I provide all information, all information step by step, how to leverage deep learning on Zynq Ultrascale Plus device. So let's start with DPU integration. So here I have my block design for setup. So this is a processing system with DPU, deep learning processing unit integrated, and clock wizard. So let's start with repositories that I have here. So in my repository I have one additional folder. It's a build folder where I have both Vivado and Linux project pre-built. So in order to build Vivado project, make should be call with the target corresponding to my board and XA in the end. So XA, it means that for Vivado project. For Linux, for Petal Linux, should be in the end used. Okay, since I have already my Vivado project built, we can go to the Vivado design, Vivado ADI, and to see how it's organized. So yeah, but before I would like to pay attention on resources. So since setup that I'm using is based on Zynq Ultrascale plus 2 CG device, I have some so the following resources available. Block RAMs, it's 150, no Ultra RAM blocks, and DSP slices 240. It's very important because depending on resources, corresponding DPU architecture should be chosen. Description of DPU IP core itself is available in product guide 338. I highly recommend to pay attention because there are a lot of very useful information about setting parameters, about connection, and so on. So according to the project guide 152, architecture can be fit into my hardware design because it consumes 121 block RAM, so and I have 150 and 222, and here I have 240. Okay, let's go to Vivado. Vivado project that I have already opened here. As I mentioned before, it's processing system, DPU, and clock wizard. So let's start with clock domain. So here I'm using 3 main clock domains and therefore 3 processor system reset IP cores for every clock domain. So first clock, it's 100 megahertz. It's the slowest clock in the system. Second clock, let's go to the clock wizard, is delivered by clock wizard, and there are 2 clocks I delivered. So first it's a 325 megahertz and 650. 325 megahertz clock is used by DPU for master axis infrastructure. 650, or in 2 times faster, it's a clock that is used by DPU for DSP slices. Why basically so? The answer is quite simple. So DSP slices operate on higher frequency than axis infrastructure. So that's why basically here we are using 650 and 325. And the next question, why basically is in 2 times faster, but not, for example, in 1.5 or in 3 times? The answer also is quite simple. DPU IP core utilize DSP slices in DDR mode, double data rate mode. It means that data that is delivered by using axis, master axis, and DSP block, DSP slices should operate on frequency, on clock with frequency 2 times higher. So 325 against 650. Besides that, for DSP slices, I have a gated clock. It allows me to reduce power consumption. Let's turn to DPU process unit parameter set. So here I have a number of DPU cores. One architecture that can be fitted into my hardware design, and I have here enabled softmax core. If we go to advanced tab, so here I have independent axis and slave axis and master axis. Why basically so? So slave axis interface is used by DPU in order to get control commands. So it's a slow, it's a very slow rate. So that's why actually this is a 100 megahertz clock domain. So master operates in higher frequency, 325, because the master interface is used to transfer data and instructions. So therefore, it's a 325, and that's why I made them independent. let's go to summary. In summary, what can be seen here that DSP slices and block BRAM amount is different that was stated in product build. Why so? The answer is quite simple. So because here as softmax cores are enabled, so softmax core implementation also required some additional resources. If I disable softmax core, in this case, amount of resources will be like it was stated in project build. Yeah, but nevertheless, I will have here a softmax core enabled, and even though with softmax core enabled, I still able to fit this DPU processing unit implementation into my hardware design. Another point that I would like to pay attention here, it's data width of Axin interfaces. So it should correspond to data width of interfaces, of corresponding interfaces in the processing system. Okay, let's pay attention how how the DPU connected here. So slow speed interface axis connected to master low power domain, and in 100 megahertz clock domain. So master interfaces connected to high performance, coherent, and low power domain also, and all these slave interfaces are fed by 325 megahertz. And yeah, so DPU clock that as mentioned before is fed by 650 megahertz. It's for DPU slices. Two interrupts is used here, so, and two interrupts connected to my interrupt port of processing system. And also what I would like to mention here, it's address editor. So what may be important here, that DPU occupies 16 megabytes. So therefore 16 megabytes, minimum 16 megabytes should be allocated for DPU IP core. So let's turn to Linux deployment. Linux deployment is done by leveraging PetaLinux from Xilinx. In order to experience Vitis AI library in Linux, some additional packages receipts should be used. So these receipts are available in DPU archive. So this is the archive for DPU IP core, and in the archive can be found folder project Vivado software meta Vitis with all necessary receipts that should be copied into your PetaLinux project. Afterwards, configuration file, via configuration file, all these packages should be enabled. So I already did this in my repository, so therefore you don't need to copy. It can be found directly in PetaLinux folder for corresponding board. So afterwards, PetaLinux can be built, then boot bin file should be generated, and finally image for micro SD card also can be generated. Yeah, let's go to my repository, since I have already pre-built PetaLinux project in build folder. So we need to go cd build t Linux here. Here I will highlight some features, some settings of the PetaLinux project. More detailed description can be found on my website. Okay, so let's start with configuration, PetaLinux config. So here I have, first of all, image packaging configuration. So because I would like to use micro SD as a boot device. So besides that, here I have yeah, and for this, of course, I need to specify arguments for kernel boot arguments in device tree. So that I did here. So and some default settings, for example, Ethernet settings. I prefer to use static IP for SSH connection with my board. I guess maybe this is all here. So yeah, sorry, exit. Yeah, let's go to another section. It's beta Linux config also, but it's C root.fs. So first of all, about user packages. This is the user packages that already available in beta Linux project by default, and you just need to enable this, or were added, like for example, Vitis AI library via receipts that can be found in the DPU archive. So besides that, if we go to apps, here can be found one additional. It's a ResNet application. This ResNet application, it's example for object classification by using ResNet 50 convolution neural network. Okay, so as I mentioned before, more detailed explanation, description of beta Linux project can be found on my website. So in the end, what we should get here if we go to CD, images, and Linux. So in this folder, beta Linux CD image file is placed. This is the file that should be flashed on micro CD card and can be used as a boot device for Zynq Ultrascale Plus. So in this section, I will show how to run examples for object classification and detection with ResNet 50 and YOLOv3 on target with Linux that we just deployed. Okay, so this is the architecture of network that I would like to use as example. So this is basically some basic information about layers, about this convolution networks, and this is my setup that I'm going to use. So this is a carrier with connected Ethernet, a USB camera, and micro SD card from where I will boot. And yeah, so here, for example, I just put a picture object detection with YOLOv3 and USB camera. So let's start from Linux. So since I have already on my micro SD flashed Linux, so I can run this on the target. So I'm using COM port here. Let me just turn on and okay, Linux, it's a boot started. Just waiting for a while until Linux is booted. We will just increase a little bit here. So, and let's go to our VCA. So, okay, so, okay, I guess ready. Yeah, so ready, there is no password. Yeah, so since Linux is ready, I will switch to SSH. For SSH, I will need SSH X11 forwarding, so with X and then root 108.8.23. Okay, let's go. Password root. Okay, here we are. So we are logged in successfully. So by default, some, okay, so these folders will not be here. I will just delete this. YOLOv3 and let's delete this archive as well. So we don't need this one right now. Okay, so by default, when you have Linux boot, so only one folder here will be created. It's an application folder. So this folder consists of example of object classification with ResNet 50. But before I will run this application, let's check if we have our DPU running on the target in our Linux, if our Linux recognized DPU. For doing this, I will use a tool from Xilinx. It's a DPU, the DPU util, and yeah, query. Let's do like this, query. Okay, let's do. Okay, and so it returns information about our DPU. So basically, it's about architecture that is used in our DPU IP core, and about clocks, architecture, and about clocks. So therefore, we can start with an example. For example, what we will need, go to CD application, so in this folder, and here we have Inc folder with images that can be used for example, and ResNet 50. It's a compiled model already for our DPU, and the binary file itself is in model binary, I guess. Model. No, sorry, it's not in model. It's in samples. It's in samples binary. Yeah, it's a ResNet 50. So in order to run, so what we will need just to call one. We will need to call our binary file samples ResNet samples. Sorry, bin ResNet 50, and one of the images. So image. Let's take this bell pepper, for example, the first one, bell pepper, and let's run. Okay, yeah, it's a fail. Of course, this is an expected error because it says us that it's about fingerprint error. So, and it says us that please recompile X model with corresponding fingerprint. Fingerprint, it's architecture of DPU. So basically, this message points us that we are using X model. X model, it's a compiled file for certain architecture, in this case for B4096, but we have B1152. So in this case, we have to recompile quantized ResNet 50 model by using corresponding architecture. So okay, so for doing this, we will need go. So for what we will need for doing this, we will go a little bit higher. So, and here I have Vitis AI folder. This is from Zynq repository. I have to go here, for example, and in Vitis AI folder, I just will open website of the Vitis AI folder. Okay, so here we are. We are using here we are using 3.0. Then we go to model zoo. And here is a model list. In model list, we are interested in two models, so ResNet 50 and YOLOv3 by TensorFlow. So for TensorFlow, I will use here. Okay, let me. Sorry. Okay. 60. Yeah. Okay. So this one, I will use this one model. So in file here in this folder, YAML file with model description, and another one, it's a YOLOv3. So basically there is a model YAML file as well. If we open this file consists of a list of trained model, and also there are a lot of different, there are several download links. We need quantized model. Since model we need already quantized model in order to recompile according to our DPU architecture. So in order to download this quantized model, this link should be used. So the same way I will use for YOLOv3. So also there is a link for quantized model, but besides quantized model, I also will need already compiled X model for the two devices. So therefore, two links here are required. So, and one more link here. It's a link. It's a link can be found in Vitis AI library guide. So this is a link. This is a link for images that will be used for trained model. So okay, let's start. I already downloaded all these archives. So it's a 4 archives. So precompiled model for ResNet 15, also precompiled model for YOLOv3. So V3, sorry, for also compiled model for YOLOv3, and the Vitis AI library samples images for pre-trained models. Okay, so So what next? So the next I will run Docker, because Docker environment provides me operation system and all necessary packages in order to recompile pre-trained models. So for doing this, I will need to run Docker itself. So before I run Docker, also I would like to pay attention that here I have arch.json. So this file was copied from build Vivado project in from the repository. So it's a YOLO build te xa file, and let me do like this. So it's a file ls. Let's do like this, yeah. xa file, then here are top gen. Oh, sorry, top gen sources, block design. Okay, let's do another little bit way. Block design, sys IP. So sys IP, sys IP, sys DPU. So, yeah, so and here is file. So this file I just copied from here directly into the folder where I downloaded Vitis AI repository. So okay, so and therefore, so yeah, so this is a file. So this file I will need in order to recompile quantized model for my target. Okay, let's go. Let's run Docker. So let's run a Docker here. So okay, Docker for TensorFlow. Okay, it's running, and what I will need next. Okay, ready. So our workspace corresponds to Vitis AI root directory from repository, and therefore what we will need, so currently I will need to unzip this ResNet 50 archive that consists of quantized model for ResNet 50. Okay, let's do this. So unzip and then tf. Okay. Okay, here we are, and we can go. This is a folder. We can go directly to this folder, tf ImageNet. So let's see what we have here. So here I have quantized folder. So this is the most important file that will be used. This is a precompiled models. Sorry, quantized model that will be used in order to recompile ResNet 50 for our architecture. So for doing this, I will use YE TensorFlow. That's this one. Okay, so YE, I will call YE TensorFlow. Architecture, I import architecture that JSON file that I copied from Vivado project. Here I point quantized model, and out dir will be created with ResNet 50.x model file. Okay, let's start it. It takes a little bit time. After our file will be ready, we need to copy it in the, we need to replace it in app folder. So, okay, so here we have ResNet 50. It can be removed, ResNet 50x model. Okay, and then let's wait for a while. Okay, it's ready. Let's see what we have here. So here I have output folder, I go to just out folder. Okay, and here I have ResNet 50x model. So just copy this cp and scp net 50x model root 108 and the folder app. Okay, password is password is root. Okay, here we are, and yeah, we can go to the target. Let's check. Yeah, here we have ResNet 50. Okay, we can run our example one more time, and let's see. Okay, yeah. So in this case we are succeed, and the picture recognized wallpaper with probability 0.99. So yeah, let's check another with another picture. For example, what kind of pictures here we have? Gray fox, for example, gray fox. Okay, yeah, probability a little bit lower, but nevertheless it works. Okay, so this is about ResNet. Also similar can be done for other pictures here. So let's go to Irish doc. Yeah, so Irish here. And the last one, probability not so high, by the way. And another one, it's Jenkins Fisher. Okay, let's go like this. Okay, so yeah, it works. Nice. Okay, the next step is how to use YOLOv3. Since YOLOv3 it's an example that is not included in the package. So, and for this we have to go again back to our Vitis AI workspace. Okay, so and here I still have several folders. So folders, I will need folder with images, with examples, in order to recompile, in order to run, that can be used in order to run the model. I have here also quantized model, and I have already compiled model. So let's unzip all this here directly here. So all these three archives. YOLOv V. So let's start with YOLOv V3, for example, one, then YOLOv V3 target. Okay, yeah, here we have quantized model, then precompiled model. Yeah, here I have also two folders with precompiled model, and the last one it's Vitis AI library images. Vitis AI library images. Okay. And okay, done. Okay, so what we have here currently. So here I have again precompiled model for my TensorFlow YOLOv V3. Also here I have compiled model, quantized model, and two compiled model. So compiled model, and besides that, here I have two new folders. It's a samples and samples links that I will use for model examples. Okay, let's start with recompiling. So basically, it's the same as we did for ResNet 50. For doing this, I have to go to the YOLOv V3 folder, and let's take a look. Its structure is completely the same. Here is quantized here we have quantized model that we used in order to recompile and get X model file. So let's do this. For this, we will need the same command, and yeah, this one I will use here. Okay, so yeah, the structure is also the same. Here I point arch that I'm going to use file, quantized model file, output dir, name of my recompiled model, and I have some extra options, and particular. So namely, this is a shape of image that I will use in my network. Okay, let's go. It takes time. Begin to compile. Okay, here I will pause video. Okay, so ready. Let's check. We have again out folder, and in out folder there is a YOLOv V3 Vodka TensorFlow.xModel file that we are basically need. Okay, so before okay, let's go to the target again. Here on the target, I will create a new folder. Dir, let's make a dir. Let's call it YOLOv V3. Okay, and we can do this, and let's copy two files. So basically here we need two files. I will copy cp out YOLOv3 model to root 3 and YOLOv3. Okay, root password. Okay, let's check. Oh, sorry. Yeah, so okay, I have here the file. Nice. Okay, what else I need? Also I need another file that can be found in compiled YOLOv3 model. In this case I have to go YOLOv3 df. So yeah, here we are, and here's file. What I will need, it's proto.tx. So this file also should be copied. It's proto.tx on the target. These three. Okay, let's copy and let's check if we have everything here. Yeah, so therefore we have already two files here. So next we need sources for our examples, for our YOLOv3 example that we will compile on the target. For sources, before, yeah, I have to go again one level here in workspace. And for sources, what I will need, so first of all, I will need to copy samples that I delivered that were delivered from Vitis AI library into example folder for corresponding model zoo. So here we have example folder. So what I will need, so I will need to copy this one. So it's from samples YOLOv3, all sources, all images I will copy to my library samples YOLOv3, where I have C++ sources for my example. Okay, let's copy it. Ready? And afterwards, I will archive this folder in order to unzip later this on the target. Let's archive. Okay, let's start here. Okay, ready. And therefore we have here an archive that yeah, we can, so we need to copy this on the target. Let's copy this. YOLOv3 target. Sorry, here we are. Okay, let's go here. So let's check. Yeah, okay, nice. Here I have already folder. Okay, let's unzip this in our YOLOv3 folder. So I just will remind that here I have YOLOv3. I have only two file proto.tx model, and I will unzip this archive also in YOLOv3 directory. So I need this. Target, and this is in a directory. We will need YOLOv3. Okay, let's sorry, I have to change their argument. It's X instead of. Okay, here we are. Okay, let's go to YOLOv3. Yeah. Okay, so besides two files that were copied earlier, here I have C++ sources for my example. So, and what I will need currently, I need to recompile. I will need to compile the sources into binary file in order to run the example. So for doing this, I will use build sh shell script. Okay, and just can run build. Okay, it takes time. Okay, so ready, and here we have some compiled binaries. So how to use these binaries? This information can be found here in the README file. So if we take a look at this README file, so yeah, it can be seen here that let's set number. Let's do like this. Yeah. So yeah, how to use this one? For example, here is an example. What kind of which binary can be run, so how it should be run, so and with for example arguments. So I will run two examples here, for image example one and another example, I guess here is not pointed, for video, for USB camera. So yeah, this is a test video YOLOv v3 example. So okay, so yeah, it means that we have test JPEG YOLOv, test performance, and test video. So and then so first parameter followed must be with model number. Okay, so name model of my here should be. Okay, let's check how it works. And then we have to go and yeah, let's run JPEG first. Okay, test JPEG YOLOv v3, then YOLOv3 X model we will need, and sample YOLOv3 JPEG. Okay, let's check. Okay, yeah, nice. It works, so at least we got no errors here, and yeah, so and we got some results here also. Let's check. If we check, so output is 0_sample result. If we pay attention on this result, so this is a picture. Is let me open this picture. I copied already on my desktop, and therefore, yeah, I can open this. Not this one. Let me another one. Photos. Okay, here we are. Okay, this is basically results itself. Yeah, so this is a result with detected car. So it means that picture was without this result, but this is the outcome. Okay, let's go and check another what I would like to check here. It's test video. Okay, yeah. So here I have compiled also binary, and for test video I will run. Let me find this JPEG here. Okay, nice, and test video. Okay, yeah, for test video I will execute this binary file, and yeah, let's see. I will run. Here we are. Okay, let's run. Pipeline will start, and window should be opened here. Okay, yeah, here we are. This is a video. I have here, yeah, so basically this is my setup connected, and I'm using here just one of the picture from YouTube channel. Okay, let's check in real time. Yeah, it can be seen how it works in real time. Yeah, so here can be seen how object detection is working in real time. That's so. Okay, so okay, so that's all for today lessons. I hope it was very interesting, and I wish you good luck with yours Zynq Ultrascale plus devices and deep learning. Ciao.